Hi, and welcome back to Atomic Math. Today we're going to talk about projectile motion. And last time we talked about linear motion. Now, projectile motion is often considered to be more complicated, but if you can do linear motion, you can do projectile motion. Let's take a look at what projectile motion is. Basically, it looks like this. But we can always take that vector and break it into its x component and its y component. And once we do, we can treat the two directions completely separately, almost like they're two different questions. So if we break it into two parts, we're going to make it a lot more simple. So we need the horizontal part and we need the vertical part. So let's take a look at a question that's going to be kind of a continuation of the question we did last time. Last time we just threw the rock straight up and it came down and hit the water. This time we're going to be throwing it out at an angle. You're standing on the edge of a pier. You toss a stone at a 30-degree angle. When the stone leaves your hand, it has an initial velocity of 10 meters per second, and your hand is 5 meters above the surface of the water when you release the stone. How far away from you will the rock hit the water? So we're going to start with the same plan as we did last time. We're going to calculate how far up the rock is going to go before it stops moving. So basically, the vertical component of this question is going to be very similar to the vertical component of just a linear question. It's just that when we're done with that, we're going to then go and look at the horizontal. We want this delta x right here. So like I said, we're going to start with the vertical, so we have to break our vector into our components, which of course is our x component and our y component. So to find our x component, we're just going to do 10 cos 30 degrees, which will give us 8.66 meters per second. And for y, we're going to get 10 sine 30 degrees, and that will give us 5 meters per second. As I said, we're always going to start with that vertical component. I have our equations here from last time, and this question has not mentioned time. And at the moment, I'm not looking for time. So I will use the equation that doesn't require time. When you look at this equation, we know the initial velocity. We know the final velocity because gravity is going to make it 0. And we know gravity. So we can solve for our delta y. And in this case, it's just the delta y up. So if we fill that in, we can see that our final velocity is 0. Our initial velocity was 5 meters per second. And we divide by 2 times gravity. That leaves us with 1.29 meters. So that little yellow arrow above your hand, that's going to be 1.29 meters. And that means that the delta y down must be minus 1.29 meters minus another 5 meters. So now we know how high the arch is. We know how far down the rock has to come before it hits the water. So we want to use this information to find out how long, time-wise, it takes for the rock to hit the water. So we'll use this equation here. And you can see that the initial velocity, because we're starting at the top of the arch, is 0. So this first term, that's just going to disappear. And once we rearrange this for time, we get this. So we'll just have 2 times delta y over the gravity, and then we'll square root that. So we're going to get 1.13 seconds. Now that is just the time for the rock to come from the top of the arch down to the water. We have to also include the time it took to go up. So we calculated the distance up, but we didn't calculate the time yet. So we're going to use this equation here. We know that the final velocity is 0. The initial velocity is the 5 meters per second. And of course, we know gravity. So we can solve that to be 0.51 seconds. So that means our total time in the air, the total time the rock is in the air, is 1.64 seconds. So we're going to put this up here. And now we're going to use that time. Now that we know how long the rock will be in the air, and we also know the velocity in the horizontal direction. And remember, nothing is going to affect the horizontal direction. Of course, we're ignoring drag, but gravity has no effect on it. So with the exception of hitting the water, it would continue at a constant velocity if it didn't hit the water. So we're just basically going to be seeing how far can we go in 1.64 seconds. I'm going to use this equation here. And the initial velocity, of course, is our 8.66 meters. And it's also our final velocity because there's no acceleration. And because there's no acceleration, this last term here is going to disappear. So my equation is simply my velocity times my time. which is 8.66 meters per second, times 1.64 seconds, which is going to give me 14.20 meters. Now, that wasn't that difficult when it was broken down. Of course, the trick is the ability to break it down. The picture makes a huge difference, and you just have to think of it as two separate questions. Of course, you have to know what you need. Generally, you're going to want to find out the time that the rock is in the air so that you can then use that in the x direction to see how far it can go. You're going to start in the vertical direction. Somehow you use the vertical to give you time, and then you can apply that time to the horizontal direction. So let's just kind of take a look at the steps that we use in a question like this. So first step, of course, we broke the velocity into its x and y components. We calculated the height in the up direction, and we used this equation here. Remember that the v final is 0 meters per second at the top, because that's the moment that gravity is going to start pulling down. If you're starting on a higher surface like we did on the pier, make sure to add that distance to the initial height to get the proper drop. All right, so you want to solve for time both up and down. We'll use this equation here. And then once we got that time, we just solved for delta x by using this equation. Now there's a couple different equations you could use, but this one's I find easiest because there's no acceleration and that term disappears. And of course, always remember that horizontal, there's no acceleration. There's only acceleration in the vertical direction. So I hope that kind of made projectile motion a little simpler. Like I said at the beginning, if you can do linear motion, if you can do up and you can do across independently, then you can do projectile motion. If you found this video helpful, go ahead and hit like. And if you want to see more videos like this, hit subscribe. And we'll see you in the next video.